Hi, greetings to our lovely lecturer, Dr. Julana. My name is Zakwan Harid. My number matrix is 297266, and this is my group member. Today, I will explain about our project, which focus on two graph traversal algorithm, which is breadth first search (BFS) and depth first search (DFS). We have been given three different graph structure named Appendix A, B, and C. Each appendix represents a different graph configuration, and we use this to demonstrate how BFS and DFS work in both recursive and iterative forms. An implementation perspective, we developed the entire project in Java. The project includes four main classes, which is the first class called project.java that runs the main menu, and then we got the appendix A.java, appendix B.java, and appendix C.java, which stores all their own graph and traversal logic. The graph structure is represented using an adjacency list, which uses a map to store a list of neighbors for each node. We added connections using the addEdge method. Every time this method is called, an eternal edge count is incremented to keep track of the number of edges in the graph. For BFS, we use queue to visit nodes level by level, and for DFS, we implemented two versions, which is a recursive version and an iterative version, which uses a stack to stimulate recursion. All three algorithms can calculate and display the traversal order, total nodes visited, number of edges, and execution time in nanosecond. Now, we go into the output area. When running the program, users are represented with a menu to choose which appendix graph to test. For example, when selecting appendix A and starting from node 1, the program will output something like this. The traversal orders shows the exact path followed by the algorithm. If the graph is fully connected, all nodes will be visited. The numbers of edges and the execution time also appear at the end of each traversal. From our analysis, each algorithm has its own strengths and logic. In our observation, BFS is useful for finding the shortest path or visiting nodes by level. It visits all nearby nodes first before going deeper. This makes BFS ideal for solving problems like finding distance or connections in a network. Meanwhile, DFS goes as deep as possible along a path before backtracking. This is suitable for tasks like maze solving, cycle detection, or topological sorting. Recursive DFS is easier to implement, but it uses the system's call stack, while the iterative DFS gives more control and uses an explicit stack. We also make sure that duplicate edges will not added, since all the graphs are undirected. One edge between two nodes is only counted once. For example, if we add at edge 1, 1, 2, we don't repeat it on at edge 2, 1. Lastly, we use system.nanotime to measure the execution time of each traversal, allowing us to compare their performance. In conclusion, our project successfully demonstrates the differences between BFS and DFS in exploring graph structure. By applying these algorithms to three different appendices, we were able to compare traversal path, edge counts, and execution times. So, that's all from us. Thank you.